Our second speaker, Zdeněk, he will be from Charles University, coming all the way from Prague, near Prague, telling us something about Z3 flow critical graphs.
Okay, thank you for invitation. So this is based on a joint work with Bojan Mohar. And so, okay, let me first explain what are the flow critical graphs, how they are motivated, and why do we care about their density. And well, basically anything in the topic of nowhere zero flows is motivated by graph coloring. So let's start with the related notions in the setting of graph coloring. So we will consider the ordinary proper coloring using some number of k colors. So you can you need to give each vertex of your graph one of these k colors in such a way that no two adjacent vertices get the same color. And a very important notion for the study of graph coloring is the notion of criticality for k coloring. So we will say that a graph is critical for k coloring if every proper subgraph of G is k colorable, but G is not. And the motivation for this definition is, well, these graphs that are critical for k coloring are just minimal non-k colorable graphs, meaning that they are precisely the obstructions to k colorability, in the sense that the graph is k colorable if and only if it doesn't contain any of these obstructions as a subgraph. So in case you are able to say something interesting about these graphs that are critical for k coloring, it will automatically imply some interesting results about k colorability. And just a notational remark, what I called critical for k coloring is usually called k+1 critical, but I actually don't like this way of saying it too much, because it means that you are constantly adding and subtracting this +1, and it's more confusing than useful. So anyway, so how can you get some interesting graphs that are critical for k coloring? So of course the basic example is the clique of size k+1. If you get a clique of size k+1, obviously you cannot color it using k colors. But if you delete a single edge from this clique, you can give the two vertices that were previously adjacent the same color, and now you can color it using k colors. So it is critical for k coloring. And then there are some constructions that you can use to create a larger critical graph. So one interesting one for this talk will be the OR construction, which is basically drawn at the top of the slide. So how it works is you take one graph, in it you select a vertex, and you split the vertex into arbitrarily, you divide its neighbors into two groups and split the vertex into two. Then you take a second graph from which you delete an edge, and then you glue the two split vertices in the blue graph in G1 on the previous ends on this edge, and the resulting graph G is called a OR sum of these graphs G1 and G2. It is very easy to see that if neither G1 nor G2 is colorable by some number, let's say C of colors, then the OR sum also is not C colorable, because if I get a proper coloring of G, then either the two black vertices receive different colors, in which case this also gives me a proper coloring of the red part of G2, or they receive the same color, and so that would give me a proper coloring of G1, because now I can merge the two vertices back together. It is not necessarily the case in general that this or some that if G1 and G2 are critical for K coloring, then G2 is as well. For example, because it may be the case that after I split that vertex in G1, the resulting graph still is not K colorable, in which case, of course, G would contain this blue subgraph plus black vertices as a proper subgraph that is still not K colorable. But there is some important case where this actually doesn't occur. So let's say a graph is K-OR, if you can obtain it from these OR sum operations, starting from copies of clique on K vertices. And it is not completely trivial, but it is possible to prove that every 4-OR graph is actually critical for 3 coloring. So if you start with cliques of psi 4 and glue them together using this operation in any way you want, you will be getting larger and larger graphs that are critical for coloring. And well, my talk is about density of critical graphs. So what can you say about the density of these critical graphs for K coloring? So it is a very basic observation that if you have a graph that is critical for K coloring, it must have minimum degree at least K, because if you have a vertex of smaller degree, you can just delete it. Because of the criticality, the resulting subgraph will be K colorable, but then you can greedily color the deleted vertex as well, and you will get a K coloring of the whole graph, which is a contradiction. And actually, there is a critical graph which doesn't have any vertices of larger degrees, and namely, this is precisely the clique with K+1 vertices, which is K regular. But already Galay in the 60s observed that this is actually the only example of such a critical graph, and that any critical graph different from the clique must have larger density. So what he proved is this bound of K plus something, which is on the order of K plus 1 over K. And this bound was slowly improved. So Krivelevich did some fairly small improvement, which stays on the same order of magnitude. And then Kostochka and Stibitz basically doubled this second term, so they got to the order of K plus 2 over K. And then Kostochka and Yancey proved this bound of type K plus K minus 2 over K plus something which decreases as the size of the graph gets down. So they proved that very large graphs that are critical for K coloring must have average degree at least K plus K minus 2 over K plus minus something small. And this is actually optimal. This is precisely what happens for these K-OR graphs as they grow to infinity. Their average degree goes to this K plus K minus 2 over K. So we now know this essentially exact answer about how dense the graphs that are critical for K coloring are. Also, why is this actually interesting? Why is this useful? Why that people spend so much effort in ascertaining this? Well, this fact that the critical graphs are dense is useful when you study the coloring of graphs, some graph classes which are conversely known to be sparse, because then you know that actually you cannot fit that many of these critical graphs into this class of graphs, and that tells you that the K-coloring in your graph class is characterized just by these few small obstructions. And the kind of maybe the most interesting or most popular example of this concerns graphs on surfaces. So just to recall, you have two kinds of surfaces, orientable and non-orientable ones. Orientable ones are essentially just spheres on which you attach some number of handles. So the examples are a sphere or a torus or a double torus and so on. And the other examples are non-orientable, which are obtained from spheres by adding cross caps. And the examples are projective plane, Klein bottle, and so on. And each of these surfaces is associated with genus, or more precisely, I will use the Euler genus, which is defined for the orientable surfaces as twice the number of handles that you added, and for non-orientable ones as just the number of cross caps that you added. And the reason why why it is good to define it this way is that then it naturally fits into the Euler's formula for the relationship between number of vertices, faces, and edges. And so throughout my talk, genus of a surface means this the Euler genus, and we can use this to define the genus of a graph as the minimum genus of a surface in which I can draw my graph without any crossings. And using this generalized Euler formula, you can see that the average degree of any graph is at most 6 plus some term which is on the order of the genus divided by the number of vertices. So if you have a graph of fixed genus and it is very large, its average degree will be close to 6. And in case that your graph is triangle free, you can improve this constant 6 to 4. And so now, if you compare this with these bounds, so for example, if you consider graphs that are critical for 6 coloring, you see that already by the result of Galai, their average degree is larger than 6 by this factor of plus 1/6. So if your graph were large enough, then this O of G over N factor would be smaller than this 1/6, and so your graph couldn't be possibly critical for 6 coloring. So this shows that for any fixed genus, let's say B, there are only finitely many graphs of genus at most B that are critical for 6 coloring, and analogously by the second result, there are only finitely many of those that are triangle free and critical for 4 coloring. And so as an example of consequence of these results, for any fixed genus, you can test, let's say, 6 colorability of graphs of this at most this genus in polynomial time, just by going over this finite list of obstructions, finite list of graphs that are critical for 6 coloring, and checking whether they appear in your graph as a subgraph or not. or another way how you can say it, a graph of bounded genus is 6 colorable if and only if all of its subgraphs of some bounded size are 6 colorable. And there are like numerous other applications of these density results in this setting of say coloring graphs on surfaces or in other sparse families of graphs. And well, let me finally mention a beautiful result of Kostochka and Yancey, who actually gave an exact bound for actually for wide range of various values of a number of colors and size of the graph, but in particular for the case of 3 coloring, they give this beautiful exact result that if a graph is critical for 3 coloring, then it has at least 5n-2/3 edges. And they also prove that these 4-OR graphs are the only graphs which achieve this bound. So you can actually improve this bound by 1 in case, 1/3 in case that H is actually not one of these 4-OR graphs. Okay, so that's for what I wanted to say about the coloring. Now, what you can say about well, how does it connect to the flows? So let me first give a couple of definitions just to recall them. So for given some abelian finite group gamma, a gamma flow is a function which assigns values from gamma to orientations of edges from your graph, which you view as the amount of flow that goes along this edge in some direction. So one possible way how to say it is using this this first condition, which tells you that the amount of flow that goes along the edge from left to right is opposite. So can be also seen as the opposite amount of flow going from right to left. And the more important condition is the second one, which tells you that the flow is not created or lost anywhere. So if you have a look at any vertex and you sum up the amount of flow leaving that vertex or entering that vertex, it will be 0. And we say that the flow is nowhere 0 if actually you do not use the value of 0 on any edge. And famously, that proved that if you have a look at a, let's say, connected graph drawn in the plane, it is k-colorable if and only if its dual graph in the plane has a nowhere 0 zk flow. So this connects the flows to k-coloring, at least in the setting of planar graphs. And that also observed that actually many of the results that work just for planar graphs seem to also work in some way in this dual setting, but now not just restricted to the planar graph, but to all graphs, which is kind of an intriguing observation, because it might mean that you could prove something for flows in graphs in general, perhaps using some transformations that wouldn't be possible if you were restricted to staying just within planar graphs. And then this would give you as a corollary these results in the planar graphs that you desire. So he made some very famous conjectures The first one of them is the 5-flow conjecture, which can be stated as the fact that every 2H connected graph has a nowhere zero Z5 flow, which would imply by this duality that every planar graph is 5 colorable. So the reason why he couldn't go for the ultimate grail for the 4-color theorem is unfortunately that the Petersen graph doesn't have a nowhere zero Z4 flow. But in an effort to fix it, he proposed the conjecture that if you take a 2H connected graph and forbid the Petersen graph as a minor, you will get a nowhere zero Z4 flow. So this 4-flow conjecture would actually imply the 4-color theorem. And finally, he conjectured that every 4H connected graph has a nowhere zero Z3 flow, which would imply the Gréchy's theorem that every triangle-free planar graph is colorable. And unfortunately, all of these conjectures are still very much open. But there are some partial results that we know. So, for example, Seymour proved that 2H connected graphs have nowhere zero Z6 flows, so just one above the bound that we would like to do. The 4-flow conjecture was proved for subcubic graphs. It is known that 4H connectivity is enough to imply existence of a Z4 flow, and actually quite recently it was proved that 6H connectivity is enough to imply the existence of a Z3 flow, which actually is quite close to proving this last conjecture, because it is known that if there is a counterexample to the 3-flow conjecture, there is one which is 5H colorable. So again, it's just by one in this H connectivity from what we actually. Okay, so as we have seen this study of critical graphs and their density is quite useful for in the coloring setting for various coloring problems. So can we somehow use something like that as in the setting of flows as well? Well, so how would you define the flow criticality? Well, obviously we want this duality for planar graphs to guide us here. So we know that for plane graphs, K colorability in the original graph corresponds to existence of nowhere zero flow in the dual. And if we want to delete edges or go to a subgraph in the original graph, it is easy to see that in the dual graph, it corresponds to contracting edges or to going to some contraction of our graph. So this leads us to our definition, or to a definition. It's actually not ours. It was known before. It was proposed by Lucchese, I think. I'm sorry if I attributed the wrong person. Sorry. So we say that a connected graph is gamma flow critical if G doesn't have a nowhere zero gamma flow, but every proper contraction does have it. And as an observation why this is a good definition, a graph has a nowhere zero gamma flow if and only if no component of G has a gamma flow critical contraction. So again, these gamma flow critical graphs serve as obstructions to having a nowhere zero gamma flow, although now using maybe slightly more complicated notion of contraction. So it's somewhat harder to check whether your graph contains this gamma flow critical contraction than it is to check that it contains some subgraph maybe. Okay, so what can you actually say about these flow critical graphs for various groups gamma? Well, it turns out that there are actually surprisingly few groups for which the notion actually is interesting at all, because well, Seymour proved that every 2-edge connected graph has a an over zero gamma flow for every group of size 6, or more generally for every group of size at least 6. So for your graph to be gamma flow critical for a group of size at least 6, it must contain a bridge, and in that case it contains K2 as a contraction, which actually is gamma flow critical. So basically the Seymour's result is equivalent to the claim that K2 is the only gamma flow critical graph for any group of size at least 6. And similarly, the 5-flow conjecture is equivalent to this also holding for Z5. So if the if the 5-flow conjecture is true, there are no interesting Z5 flow critical graphs. Also, you can easily characterize Z2 flow critical graphs, because well, a graph has an over zero Z2 flow if and only if it is Eulerian. So equivalently, if and only if it doesn't contain an edge cut of odd size. And so this shows that Z2 flow critical graphs are precisely those that are 2 vertices joined by an odd number of edges. So this leaves as the interesting cases only the groups of size 3 or 4, Z3 and Z4. And just as a remark, it is known that the existence of nowhere zero Z2 square flow is equivalent to the existence of nowhere zero Z4 flow. So it doesn't matter in this notion which group of size 4 you choose. And so the density of Z3 for critical graphs was studied recently by Lima, Shivang, and Wu, who first of all observed that using this Kostochka and Yancey theorem and duality, if you have a planar Z3 flow critical graph, it has at most 5n minus 8/2 edges. And so you might hope to use the kind of the standard TAT-like thing and try to generalize this or conjecture that this actually holds for all graphs, not just for the planar graphs. But unfortunately, this fails pretty fast. So they also observed that if you take the graph case 3 and minus 3, and you add one more edge between the vertices of this large degree of degree n minus 3, the result will be Z3 for critical, and it actually has 3 and minus 8 edges, so significantly more than 5/2n minus something. And they conjectured that this is actually the right answer, except for some small graphs. And if their conjecture was true, this would imply this fact that in every 6-edge connected graph you have a over zero Z3 flow, because every 6-edge connected graph, or every contraction of a 6-edge connected graph, is also 6-edge connected, and therefore it has at least 3 times the number of vertices edges, which is a result which is known. It is this last result of Ovas, Thomassen, Wu, and Chang, but it would still be nice to have a different proof or this generalization. But unfortunately, they were not able to prove this. They were able to just prove this bound of number of edges being roughly at most 4 times the number of vertices. Now we have actually tried to improve this bound to go to this 3 quite hard, but we kind of failed. So we were looking for another thing to try. And we observed that, well, we noted that this graph, case 3 and minus 3 plus, has actually genus which is linear in n. So while you cannot just directly take this planar bound of 5n/2 and generalize it to a planar graph, You might be able to do it if you also take the genus of your graph into consideration. And so we did that. And so we have proved this result, that if you have a Z3 flow critical, then it has at most 5 times n plus 5 times the genus minus 8 over 2 edges. So in particular, it implies that the counterexample to this conjecture has to have necessarily a linear genus. And actually, we proved something slightly stronger. We proved a result for graphs with boundary. So in this sense that you assign some boundary value to each vertex, which is the amount of flow that is created or lost in this vertex. And then in this setting, you can again naturally define the notion of contraction, where you contract two vertices, you need to sum up their values of their boundary. And then you can define the notion of flow criticality in the natural way, that it has no nowhere zero flow with this boundary, but all proper contractions have one. And it turns out that our result holds even in this case of graphs with boundary. And the fact that we consider the graphs with the boundary is well, useful in some applications, but also it is important in the proof because it enables us to use this potential method that Kostochka and Yancey used to prove the result. I will actually not tell you anything more about the proof because it's kind of technical. Just to remark that it's actually important that we work in this setting of graphs with boundary, that we couldn't do it just in the original setting. So this result of ours has some kind of applications, but mostly in reproving things that were already known but had more complicated proofs. So, for example, there is this strong variation of three-flow conjecture that tells that every 5-edge connected graphs with Z3 boundary has an over zero flow. This is obviously still open. And it was a couple of years ago by De Jong and Richter proved to hold for projective planar graphs using a fairly long, complicated proof. If you just have a look here, because if the Euler genus of your graph is 1, this tells you that it must have less than 5 and over 2 edges, so it cannot be 5-edge connected. So just directly from this, we see that this strong three-flow conjecture holds for projective planar graphs. We can also prove this strong three-flow conjecture for graphs that differ from planar graphs by adding at most 3 edges, which in some weaker way was already proved before with just one edge distance from planar graphs as an important ingredient in the proof that three-flow conjecture holds for toroidal graphs. And in particular, this implies that the counterexamples to the three-flow conjecture must have crossing number at least 4, which actually I'm not sure. There were some results along that way as well, so maybe it was actually known before. I'm not 100% sure. Okay, so what are the kind of the future directions? What are the open questions that one could study? And it turns out that there are actually quite a lot of them. This is an area that is not very much explored. So one natural question is actually what is the right dependence on the genus? The factor of 5 over 2 at the number of vertices is actually the correct one because of the duals to the 4-or graphs. But we do not know whether this constant 5 over 2 at the genus is the right one, and we suspect it is not. So this lower bound that we get from this graph K3 and minus 3 plus is that alpha must be at least 1, but we do not know where in this range it actually lies. And there are a lot of open questions if you consider the critical graphs with respect to a group of size 4, Z4 or Z2 squared. And really the situation there is seems to be much more complicated than for the Z3 flow critical graphs. So in particular, due to the four-color theorem, there are no planar Z4 flow critical graphs, which is kind of bad because if we would like to look for this bound of type number of edges is at most C times number of vertices plus some function of genus, we would like this first term to correspond to, if you forget about the last one, we would like to this correspond to what happens in the plane, but in the plane there are actually no planar Z4 flow critical graphs, except for K2, of course. Yeah, we actually don't know whether this this problem actually makes much sense. We don't know actually whether it couldn't actually be true with C being 0. I mean, what that would mean is that it would be essentially the claim that on any fixed surface there are only finitely many Z4 flow critical graphs. This might be the case. It might be completely wrong. We have no idea. We don't even know whether there are infinitely many Z4 flow critical graphs that can be drawn on the torus. And finally, let me quickly discuss the bounds independent on the genus. So there is this conjecture that for Z3 flow critical graphs, they have a number of edges which are at most roughly 3 times n. And we know that their conjecture is actually implied by this strong 3-flow conjecture, which is, I mean, probably reducing a simple problem to a much harder one. So that's not much of a help. For groups of size 4, it has been observed by Jiao Li that if you consider the let's say Z4 bordered graphs, then the right bound is that the number of edges is at most twice the number of vertices, which is tied before, because you can set up the boundary Z4 boundary on K2 and -2 in such a way that the resulting graph is flow critical. But actually, this example doesn't apply without the boundary. Without the boundary, K2 and -2 is not Z4 critical. So again, we don't actually know what should be the right answer for the density of Z4 flow critical. So we know, of course, we know that this constant C here must be at most 2, but we do not know whether it is exactly 2 or strictly smaller than 2. Okay, thank you for your attention.
Yeah, let's thank Zdeněk for the nice talk.